Hello students, welcome again in my new video, and today I am taking limitations of Bohr's model of atom after taking atomic spectra. So what were the drawbacks or limitations of Niels Bohr's model of atom? First is he could not explain spectra of multi-electronic atoms as we did, that he gave atomic spectrum for hydrogen or hydrogen-like species, meaning one electron containing species. So he was unable to give spectra of multi-electronic atoms. Okay friends. One more thing, he was unable to give Zemann's effect. Now question arises that what is actually this Zemann's effect? Students, in the line spectrum of different elements, different bright lines were obtained, as we did in case of sodium, as we did in case of hydrogen, which lies in particular wavelength region. So when on that spectral lines magnetic field is applied, they further split into finer lines. So I have written here, when magnetic field is applied across spectral lines, further splitting of that spectral line take place. So this effect is called Zemann's effect. That means splitting of spectral lines in magnetic field. Now one more effect is there, that is Stark's effect. Stark's effect, students, same is there, splitting of spectral lines, but in presence of electric field instead of magnetic. Here we are applying electric field and further splitting of that spectral line take place. So students, these were the drawbacks. Next was, he was unable to give dual nature of matter. That was given by de Broglie, and we have done it. Its derivation also we have done, de Broglie's wavelength. So Bohr was unable to give dual nature of matter. One more thing, Heisenberg's uncertainty principle. Niels Bohr was unable to give this uncertainty principle. What is that principle? I will be taking later. Next is the geometry and the shape of molecules was not expressed by Niels Bohr, and how the molecules are formed from the atoms, how the atoms have different ability to form molecules. This idea also was not given by Niels Bohr. So students, these were all the drawbacks of Niels Bohr model of atom. Now I am telling you, students, what is this Heisenberg's uncertainty principle. Firstly, as it is a principle, student, that's why it will be having particular definition. And definition is, it is not possible to measure simultaneously the position and momentum of a microscopic particle with absolute accuracy. Meaning, students, we cannot able to find out the position and the velocity or momentum of a microscopic particle simultaneously with absolute accuracy. एक साथ पोजीशन भी मालूम पड़ जाए और मोमेंटम भी मालूम पड़ जाए किसी भी माइक्रोस्कोपिक पार्टिकल का, ये संभव नहीं है. Like we are dealing with electron, that is also a microscopic particle. So we can say it is not possible to measure simultaneously the position and momentum of an electron with absolute accuracy. Okay students, I will tell you the reason also. And he gave, this Heisenberg gave a formula also, del x. What is this del x? It is uncertainty in position, and del p is uncertainty in momentum. Momentum, you are knowing students, mass into velocity is momentum. So del x into del p, this product of momentum and position uncertainties, is either greater than or equal to h upon 4 pi. Every term is a constant here, students. H is a Planck's constant that you know. 4 is again constant, pi is again constant. This formula we can simplify in different terms also, like del x. Here I am taking m del v. M del v, mass of any particle if I am taking, will be constant. That's why m comes out del v, uncertainty in velocity, will be greater or equal to h upon 4 pi. Okay, students? So, this is Heisenberg's uncertainty principle. Here I am giving you explanation that why it is not possible to measure momentum and position of an electron simultaneously. Suppose if we are observing any electron in the trajectory, any orbit shell, any electron if we are taking, to know the position of that electron, we should require some light to focus, to pinpoint the position of that electron. So, we will be focusing some light radiation on that electron to know about the accuracy of its position. Remember, students, if this light radiation is associated with lesser wavelength, more will be the accuracy in the position. I have written it also, students. Lesser the wavelength, more is the accuracy in position. Now, other thing which is related to it is, if we are providing some radiation of some lesser wavelength, we are knowing that frequency and wavelength are inversely proportional. If wavelength is less, automatically frequency will be more. And if frequency more, energy will also be more, because energy is directly proportional to frequency. E is equal to h nu we have done. So, less wavelength light we are taking, but that light will be associated with more energy. And as that energy radiation is striking to this electron, its velocity will change. And that's why we cannot able to measure the velocity or the momentum of an electron accurately. So we will be having accuracy in the position, but we will not be having accuracy in the velocity, and vice versa. If we are calculating velocity accurately at that time, the position cannot be accurately judged. Okay, students. So in this way, this Heisenberg uncertainty principle is saying that position and momentum of an electron or the microscopic particle cannot be measured simultaneously with absolute accuracy. Okay, students? One more thing which is related to this Heisenberg uncertainty principle. As we know, students, in the atom, in the center, nucleus is present, and inside the nucleus, nucleons are there. What are nucleons? Proton and neutrons. An electron is present outside the nucleus. How can we say that? How can we prove that electron is not a part of nucleus? How can we say why electron is not a part of nucleus? If, students, electron is present in the nucleus, suppose we are assuming that if electron is present inside the nucleus, then its uncertainty in position should be taken 10 raised to the power minus 15. That is the diameter of the nucleus. So that electron, if present in the nucleus, that means its position will be somewhere in the nucleus, somewhere in the diameter of 10 raised to the power minus 15 meters. Okay. So here now we are knowing the uncertainty in position, that is 10 raised to the power minus 15. So in place of this del x, we are keeping that 10 raised to the power minus 15, and we are calculating the velocity of electron. So here the formula is del x into del p is equal to h upon 4 pi. That will be further simplified as del x into mass del v is equal to h upon 4 pi. Del V in this way will be equal to h upon 4 pi into m into del x. On keeping all the values, h is Planck's constant 6.6 into 10 to the power minus 34 joule second. 4 is constant, pi is also constant, 3.14 you can take, 22 upon 7 or whatever. Mass of electron here I am taking because we are finding out the position of or the velocity of electron. So mass of electron is 9.1 into 10 raised to the power minus 31 kg. And del x we are keeping 10 raised to the power minus 15 meters. Okay. And in this way we can calculate del v, and it is coming out 5.77 into 10 to the power 10 meter per second. It is very much greater than speed of light, and that is not possible. Electron moves with the speed of light only, and this speed which is coming out here is greater than the speed of light, that is 3 into 10 to the power 8 meter per second. You are knowing it, students. So this proves that electron is not a part of nucleus. It is placed outside the nucleus. It is present in the extra nuclear part. Now students, I am taking some numericals based on dual nature of matter, that was de Broglie's nature, de Broglie's wavelength, and the Heisenberg's uncertainty principle. Today I am taking numericals on de Broglie, and in the next video we will take Heisenberg's uncertainty principle numericals. Okay, students? So, students, we are starting numericals based on de Broglie's dual nature, de Broglie's wavelength. Very simple questions I am taking here. First question is, find the wavelength of 100 grams particle moving with velocity 100 meter per second. Okay, students. So, what we are calculating here? Wavelength. And what is given to you? Mass is given to you. And velocity is also given to you. And you are calculating what? Wavelength. So here, for the dual nature, de Broglie's gave a relation that was lambda is equal to h upon mv. H is Planck's constant, m is the mass, v is the velocity. H, Planck's constant, value is 6.6 into 10 to the power minus 34, and the unit of that h we are using is joule second. It is not joule per second, it is joule second. And value of joules in kg meter, that is kg meter square per second square, and second is also there. So this second inverse, second raised to the power minus 2 and second, that will finally give you kg meter square per second minus 1 we are getting here, kg meter square per second. Okay, so this unit we will use here, 6.6 into 10 to the power minus 34 kg meter square per second, value of h, upon m. M mass is given to you, that is 100 grams. But here, if we are using kg, here also we have to convert that gram into kg. So 100 divided by 1000, that will give you 0.1 kg. Into 100 is the velocity given to you in the question, students. So when you calculate it, then you will get 6.6 into 10 to the power minus 35 meters. I am suggesting you to keep all the units here in the formula so that you can able to get final unit in the answer, that is meter here. Next question I have taken is calculate the mass of photon of sodium light having wavelength 5894 angstrom and velocity is 3 into 10 to the power 8 meter per second, velocity of light. Since photon we are taking, it travel with the velocity of light 3 into 10 to the power 8 meter per second. Here also, students, same formula will be used, but we are calculating in this mass we are calculating. Previously we calculated lambda, wavelength. So here mass we are calculating. Formula remains the same. Lambda is equal to h upon mv. Lambda is given to you, students, 5894 angstrom. We have to convert it into standard units, meter. So 5894 into 10 raised to the power minus 10 to convert angstrom into meters. Okay. This h is 6.6 into 10 to the power minus 34 kg meter square per second. That is joule second. We are converting it into kg meter square per second. Mass we are calculating, students, in the formula. Mass we are calculating here, so m, and velocity is given to you 3 into 10 to the power 8 meter per second. In this way, mass can be calculated by rearranging the values. Very simple. And finally, you will get the answer, that is 3.75 into 10 to the power minus 36 kg. Don't copy down as such, friends. Do all the calculations by your own and then write the answer, and try to do the questions without looking to the solution, because these all questions are very basic questions. Next question I have taken here is calculate de Broglie's wavelength of an electron with 1% speed of light. Here they are saying that calculate wavelength of an electron which is moving with 1% of the speed of light. Velocity is given to you, students. So here formula is again the same. Lambda is equal to h upon mv, but v here is 1% speed of light. So that we have to calculate. 1% speed of light is 3 into 10 to the power 8. So on calculating this, what we will get? 3 into 10 to the power 6. This 100 comes up with 10 to the power minus 2. 8 minus 2, that will give you 6. Exponential rules. 3 into 10 to the power 6 meter per second. Velocity hai. Now we will keep all the values, students, in the same formula. H upon mv. H is this, m, mass of an electron, because in the question they are saying de Broglie wavelength of an electron. So we have to keep mass of electron, that is 9.1 into 10 raised to the power minus 31 kg. And velocity is 1% speed of light, that is 3 into 10 to the power 6 meter per second. In this way, students, these two will get cancelled out. Second inverse get cancelled out. Meter will be cancelled. Kg will also get cancelled. And finally, we will get the unit only meter. So, answer will be 2.43 into 10 raised to the power minus 10 meter. You calculate by yourself, students. In the chemistry, students, mainly the calculations are very complex, but simple. You have to do addition, multiplication, division. They are quite long, complex, but you are knowing the concept how to do. So you have to do and calculate final answer, otherwise you will lose your marks, students. Next question, question number 4 I have taken. Calculate wavelength again for an electron accelerated by 1 into 10 raised to the power 4 volts, this time given, volts. We have to convert this volt in joules. First thing is that. Second thing which you have to observe here is an electron is accelerated. Accelerated meaning kinetic energy is there in the electron. Kinetic energy is equal to half mv square, that you have studied in junior classes, students. Half mv square. and kinetic energy value is given to you 1 into 10 raised to the power 4 volts. To convert this volt into joule, we multiply that quantity by 1.6 into 10 raised to the power minus 19. So for the conversion, because 1 volt is equal to 1.6 into 10 to the power minus 19 joules, so 1 into 10 to the power 4 volts will be equal to that value multiplied by this 1.6 into 10 to the power minus 19 joules. So this whole value we will convert into joule. Now, half mv square is equal to 1 into 10 to the power 4 into 1.6 into 10 to the power minus 19. And by this relation, you can calculate the value of v. Velocity you will calculate so that you can keep the values in de Broglie's equation. So v will be under root of this value whole into 2 cross multiplication upon m. M is of electron because electron is getting accelerated. So 9.1 into 10 to the power minus 31 kg. And if you calculate the square root and everything, you will get the value 5.93 into 10 to the power 7 meter per second. Again, I am telling you these calculations are quite tough, quite complex. Not tough, students. I should not say tough. They are slightly lengthy and time consuming, but you have to do it because here you are just calculating V, and now you have to put that V in the relation of de Broglie, that is lambda is equal to h upon mv. H value you are knowing, m value you are knowing 9.1 into 10 to the power minus 31, and V you have to keep this value, students, that you have calculated by kinetic energy relation. And thus, by keeping all the values, you will reach to the final answer, and that is 1.22 into 10 raised to the power minus 11 meters. Wavelength you are calculating, students. So in meters. Clear, students? So I have taken just 4 questions here, students. And now I will be uploading some more questions in the assignment. Do it, and if you have any problem you can ask me. I'm saying again and again, but you are not turning up, students, with your doubts. So take the classes seriously and do the assignments and the work which I am giving you in your fair classwork copy. Okay, students, for today this much is there. Thank you.